All right, today we're jumping into an absolutely epic journey. We're not talking about kings and empires, but about the revolutions of the human mind. We are going to trace the incredible story of mathematics, from the very first scratches on a bone, all the way to the deepest questions about reality itself. So yeah, let's get right into it.
Our story starts in a, well, pretty surprising place. The writer, Goethe, said this about Mozart's opera, The Magic Flute. See, on the surface, it's just a beautiful show, right? A spectacle. But underneath, for those in the know, the initiates, there's this whole other world of symbolism and hidden meaning. And as you're about to see, mathematics has a very, very similar story.
And that brings us to the big question, the central mystery of our story. What on earth could possibly connect the high art of the Enlightenment with a prehistoric artifact? Well, the answer is the story of how we, as a species, learned to think in numbers, and how that one skill has completely revolutionized our world time and time again.
Okay, so our first revolution is maybe the most important of them all. This is the giant leap from just using math as a simple tool, for counting things, to building an entire system of absolute, undeniable truth.
For most of human history, this is what math was. I mean, look at this thing. It's incredible. It's a wolf's shin bone, and it's basically an ancient spreadsheet. You've got 55 notches carved into it, and they're deliberately set up in groups of 5. This tells us that 30,000 years ago, our ancestors weren't just counting 1, 2, 3. They were organizing information. Math was a tool. It was purely practical, a way to track the days or maybe the number of animals in a hunt.
The great ancient civilizations, the Egyptians, the Babylonians, they took this practical approach and perfected it. They could build the pyramids, they could predict eclipses. Their mathematics was basically a collection of recipes and rules of thumb that just got the job done. It was all empirical. It worked because, well, they'd seen it work before. It was a whole toolkit of how, but nobody was really asking why.
And then the Greeks came along, and they completely changed the game. They weren't happy with a recipe that just worked. They wanted to build a system where every single conclusion was absolutely, logically inescapable. A system built on a tiny foundation of simple, self-evident truths they called axioms. This was a massive shift, moving away from practical observation and into the world of pure, deductive logic. And the masterpiece of this new approach was Euclid's Elements, honestly one of the most influential books ever written, period. He took all these scattered bits of geometry people knew at the time and wove them into this single, breathtaking logical structure. Starting with just a handful of basic assumptions, he proved hundreds and hundreds of theorems. For over 2,000 years, this book wasn't just a textbook on math. For most people, it was math.
So for 2 millennia, Euclid's system was king. It was perfect. But it did have one little weakness. It was fantastic at describing a static, unchanging world. The next great revolution was all about inventing the tools to understand a universe that is in constant, chaotic motion.
Just think about it for a second. Geometry is perfect for measuring a field or the angles in a building. Static things. But what about the path of a cannonball flying through the air? The speed of a falling apple? The orbit of a planet around the sun? These things aren't static, they're processes. They're all about change. And Greek mathematics just didn't have the language to describe them.
The answer, when it finally arrived in the 17th century, was calculus. And it was such a monumental leap forward that 2 of the greatest minds in history, Isaac Newton and Gottfried Leibniz, invented it completely independently right around the same time. What's so wild is how they got there. Newton, over in England, was super secretive, totally driven by the physics of gravity, and he thought about it all in terms of geometry. Meanwhile, Leibniz in Germany was open, he was driven by big philosophical questions, and he created this beautiful, simple algebraic notation that we still use today. The rivalry was intense, but between the 2 of them, they gave science its most powerful tool ever.
And this wasn't just about solving some practical problems. It was really a return to a much older ideal. The great Archimedes, who was a master inventor, was said to care way more about his abstract mathematical discoveries than any of his amazing machines. The guys who invented calculus were tapping into that exact same spirit, the pure pursuit of understanding, the abstract products of thought.
The first 2 revolutions we talked about, they built on what came before. This next one, though, this was a straight-up act of rebellion. It was about to challenge the very foundations that Euclid himself had laid down 2,000 years earlier.
Deep in the heart of Euclid's geometry, there was this one axiom that it felt different, A little weird. The parallel postulate, which basically says if you have a line and a point not on that line, you can only draw one single line through that point that's parallel to the first one. It just seemed less obvious than the others. So for centuries, mathematicians were obsessed. They were convinced it wasn't an axiom at all, but a theorem you could prove using the other, simpler axioms.
And they all failed. Every single one of them. It was one of the most frustrating problems in the history of math. Every time some brilliant mathematician thought they had finally cracked it, someone else would find the flaw. And the flaw was always the same. They had accidentally assumed something that was just a different way of saying the parallel postulate. It was this perfect, maddening, circular trap.
So after centuries of banging their heads against the wall, a few really bold thinkers, like the Russian mathematician Nikolai Lobachevsky, decided to try something completely radical, a new strategy. What if the reason no one could prove it was because it wasn't necessarily true? So he took this unbelievably audacious step. He said, okay, let's just assume the opposite is true. Let's assume you can draw more than one parallel line to that point. And then he just set out to see what kind of weird universe that would create.
And to everyone's absolute shock, it didn't create a contradiction. It created a completely new, perfectly logical, non-Euclidean geometry. It was this bizarre world where the angles of a triangle add up to less than 180 degrees, and parallel lines can eventually curve away from each other. Suddenly, math wasn't the one true description of space anymore. It was a whole collection of possible descriptions. It was a game changer.
This newfound freedom of thought, it was like opening Pandora's box. Now that mathematicians had questioned the nature of space, they turned their attention to an even bigger, even more profound concept: infinity. For thousands of years, infinity was just this vague idea, right? A symbol for something that just goes on forever. But then, in the late 19th century, a German mathematician named Georg Cantor decided to treat it like a real mathematical object. He set out to do something that sounds completely impossible. He wanted to count the infinite. And what he found completely shattered everyone's intuition. He proved, with pure, inescapable logic, that there isn't just one size of infinity. There are infinitely many different infinities, and some are unimaginably larger than others. Okay, so what does that even mean? Well, here's the basic idea. The infinity of whole numbers, 1, 2, 3, 4, and so on, is what we call a countable infinity, because you can at least imagine listing them all out in some kind of order. But Cantor proved that the real numbers, that's all the numbers on the number line, including every possible decimal like pi, that is an uncountable infinity. It's a completely different, fundamentally larger kind of infinity. It's so dense you could never, ever list all of its members. Mind-blowing, right? Now, discovering non-Euclidean geometries and different sizes of infinity was incredibly exciting, but it was also kind of terrifying. It felt like math was losing its solid ground, its claim to absolute certainty. And this led to our final revolution, a full-blown crisis of faith and a desperate search for solid ground to stand on. All of a sudden, cracks started to appear in the foundations. Cantor's amazing ideas about sets led to some really baffling paradoxes. The philosopher Bertrand Russell found one that shook math to its absolute core, a logical brain teaser about sets that contain themselves. So in response, mathematicians basically split into different camps. You had the formalists, led by David Hilbert, who tried to rebuild all of math as this pure formal game to prove it was consistent once and for all. And on the other side, you had the intuitionists, who argued we should just throw out any idea, like some of Cantor's weirder infinities that couldn't be directly built by the human mind. Here's the thing. The crisis was never really resolved. Instead, what came out of it was a totally new understanding of what mathematics even is. That old Greek dream of a single, perfect, unshakable system of truth, it was gone. And in its place was a more humble, but honestly a more exciting picture. Math as a human creation, a dynamic story of evolving ideas, constantly questioning its own assumptions. From the absolute certainty of Euclid to the mind-bending paradoxes of the 20th century, the story of math has always been about geniuses who dared to question the very things everyone else took for granted. And that leaves us with one final, fascinating question to think about. What fundamental idea in math, what truth that we all accept as obvious today,